Greetings and welcome, internet friends. Mr. Waddy here, and we're doing kind of part 2 of solving quadratic equations with the quadratic formula. And we're going to look particularly at a piece of the quadratic formula, part underneath the square root, also called the radicand. Remember, the side of a radical is called a radicand. And this piece in particular is called the discriminant. B squared minus 4ac is called the discriminant, and we're going to use it to discriminate or distinguish between possible outcomes when we're solving equations. And since it's inside the radical, you can limit its possibilities or identify its possible outcomes based on whenever it's positive. I know that that radical will give me two possible solutions. Two real solutions. Whenever it's equal to 0, the square root of 0 plus or minus 0 is going to give me a single real solution. And anytime the discriminant is negative, then that means I'm taking the square root of a negative and I will have no real solutions. I also could describe that as saying that there are two imaginary solutions. In the case of my Algebra 2 student, this year anyway, my students already know about the imaginary. So here we go. Example 3. Determine the number. So I'm not identifying the solutions. I'm just figuring out how many are there. Determine the number of real solutions. So this quadratic is already in standard form. It's already equal to 0. So a equals 1, b equals 8, negative. And the discriminant of the quadratic formula is just the b squared minus 4ac is the discriminant. And so I'm going to plug that in. So 8 squared minus 4 times 1 times a negative 3 is 64. Oh, I got double negatives, so those can pair up. And 4 times 3 is 12. And actually, I technically don't even care what these add to. I just know that they add to be positive, but I'll write down what I think the answer is, 86. And because the discriminant is 86, being greater than 0, therefore there are 2. Man, I was looking at my recording software. All right, good. Solution. I did figure out over the last couple of weeks, by the way, how to make my cursor follow me when I write. You'll see a lot of my older videos. Once I start writing, the little mosquito stays at the top. Anyways, whatever. Here we go. Determine the number of real solutions for the following. So let's set this in standard form first of all. X, both sides. I'd have a 9x squared minus 6x plus 1 equals 0. And so a equals 9, b is Charlie, equal to 1. Plug it into the discriminant. And so negative 6, careful, all squared, minus 4 times a times c. Negative 6 all squared is positive 36, minus 4 times 9 times 1 is 36. That equals 0. And therefore, that means this has one real solution. If I was to graph y equals this, it would have been one of those parabolas that ricochets off the x-axis and hits it only once. And so they didn't care what the solutions were. They just wanted to know how many are there. So let's see. Is there anything interesting going on here? Let's take a look at question 9. Tell you what, I could move the 7x and the 1 over to this side, but why? I'll just subtract the half x squared from both sides. And I can just arrange this anyway. So negative a half x squared plus 7x minus 1 is equal to 0. And I can technically plug this into the discriminant. The 4ac will actually cancel out. The 4 will cancel out with a half. But if I wanted, I could get rid of the fractions by multiplying both sides by 2. if I wanted. Just multiplying by the way, by a the least common denominator of all of your terms will eliminate any fractions. So I'd have negative x squared plus 14x minus 2. No, although now in this case, 14 squared might put it out of the range of I think a equals -1, b equals 14, c equals -2. It would have worked just fine if you used -1/2, 7, and -1, by the way. Same, it would. So b squared minus 4 times a times 14 squared, I think, is 196. I think so. Yeah. Negative times a negative times a negative. There were 2 that would pair to be positive, but 1 left over. And 4 times 2 is 8. And that looks like 188. Therefore, if that's the value of the discriminant, that tells me there are 2 real solutions. Real solves. Boom. All right. Okay, finding the number of x-intercepts of a parabola. And so in this case, I have a an equation that's equal to y. It's a function. And so I could do all the work of graphing it. They don't actually care what the intercepts are. They just want to know how many are there. And so the x-intercepts are going to occur whenever y equals 0. So 0 equals 2x squared plus 3x plus 9. And now I can do my discriminant deal. A equals 2, b equals 3, c. And then b squared minus 4ac. 3 squared is 9, minus 4 times 2 is 8 times 9 is 72. Uh-oh, this is looking negative. Oh, all right, negative 63. Woo! So that means there are no x-intercepts, right? No real solutions. Graphically speaking, no x-ints. Boom. Nice. Are any of these that cool? I'll tell you what, I'll do this one. So I'd set it equal to 0. 0 equals x squared minus x, and I'm going to write plus 0 just because would have been easy for some. So a equals 1, b equals -1, c equals 0. Oh, actually, effect always going to be. Unless b was also, no, yeah. Minus 4a c. Yeah, the multiplying by 0 for c or a is just going to zero out this whole piece. And then squaring a number is always going to give me a positive or 0. So it definitely has some, at least one real. So here's 1 minus 0 is 1. And because that's positive, I will have a real solution. Sorry, number of x-intercepts. 2 real solutions to the equation this equals 0. How many x-intercepts? 2x. Alright. Alright, and now this is where it gets cool. Mathematicians, we like to first find an accurate way to get an answer, and then we try to find an efficient way to get an answer. That's what this is all about. Like, what's the best way to use when, because mathematicians are efficiently, we're trying to do the least amount of work and get the maximum output for our efforts. So yeah, mathematicians first, you got to find an accurate method, then an efficient method, and then, if possible, you want to find an elegant method, where it's just almost poetically beautiful, the way that you solve it. That one's not as important. But here we go. So we've learned a whole bunch of different ways of solving. We've learned how to solve by factoring. When is this good? We're pretty good at factoring. It's straightforward. The problem is, not all problems are factorable. And usually real-life problems won't be factorable. Solving by graphing, man, that is not fun. Unless you have technology, right? If you got technologia, it's fine. If you don't have technology, doing it by hand, right, it lets you see the number of solutions easily. Although now we have the discriminant that could tell us that. It is appropriate whenever you want approximate solution. So it's not very accurate. And it may not give you exact answers. Using square root solving by rooting both sides of an equation can only work if I have x squared plus 0x plus and so yeah, anytime b equal to 0 is the only time this method works, where it can be written in this form. But I find generalizing it this way better. Anytime there's no middle term, there's no b term, you can subtract c from both sides, divide by a, root, plus or minus. Completing the square is my favorite method of solving quadratics, but it's a little bit annoying anytime a was something other than 1. It's also a little bit annoying anytime the middle term is odd, because you have to do the b divided by 2 all squared thing. And so yeah, it could be tedious in those situations, but it works every time. Exact solutions every. And akin to the completing the square method is quadratic formula, because we discovered this by completing the square. It works every time, gives exact solutions, but its calculations could be tedious. And so what's kind of nice, although we're still going to have a review day and a review assignment, this kind of is going to be a great summarizing experience for us, choosing a method solve. So here we go. First thing first, I'm going to set these equal. X squared minus 10x minus 1 equals 0. Is that factorable? No. There are no factors of 1 that subtract to be 10. However, leading coefficient is 1. Middle term is even. It's a great candidate for completing the square. Which, now that I realize that, I should have left the c term over there. What? Crazy. Let's do that. So I'm going to have x squared minus 10x blank equals 1 blank. You don't have to do the blank. I got to find my new c term. My new c is equal to b divided by 2 all squared. Y'all remember that formula? Yeah. It's been a while. My students happen to have April vacation in the middle of this video and a previous. So yeah, they might not remember it right off the top. And so 25 is the new c term. And so I'm going to add 25 to both sides. I fast factor this. Whoop, whoop. And so that's going to be x minus 5 all squared. And the way you get this minus 5, it's just half of your b term here. It's also the thing that I had right here before I squared it. 1 plus 25 is 6. And now the benefit of completing the square is I have one variable represented in expression, and I can get rid of this square by rooting both sides. But of course, I got a plus or minus. I wouldn't forget. Yeah, wouldn't forget it. Plus or minus square root of 26. No number goes into it. And then add 5 to both sides. So 5 plus or minus square root of 20. Now, why did I choose this? Because the a term was 1 and the b term was even. So it wouldn't be a bad idea to flip back to this little table. Try to consider when to use method. Now this over here, could I factor it? Maybe. I'd have to factor using the AC method. Are there factors of 48 that subtract to 13? I'm beginning to be suspicious that that's not. And since this is greater than something other than 1, I'm not going to want to complete the square. This was odd, and rather not complete the square. So we'll use the quad form. A equals 2. equals -3, -20. I don't know if I'll have enough room. This one's a factorable one. I can see that. All right, so here we go. Hey, I haven't sung the song in over a week. Here we go. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2. Using a new headset I just got in the mail for my Xbox One. I hopefully it's working out all right for y'all. 13 plus or minus the square root. -13 squared is 169. Double negatives become positive. 4 times 24. What? 96 times 2. I'm wanting to say 1. Oh, all right. My brain limit. Either way, I'm not going to be able to do the square root. What am I doing, guys? 8 times 24 is 192. I almost wanted to say 198, and I'm like, that can't be possible. All over 2 times 2 is 4. Equals, add that 192 and the 169 I get. And I don't believe that is what it is. Guys, you know what that means? That means the problem was factorable all along. Yeah, anytime that this turns out to be an integer, right, non-decimal sort of thing, that means the original problem was factorable. Although I still don't think I regret this choice because, yeah, the amount of time it would have taken me to find the factors of 48 that subtracted to 13, AC method. So let's see, 13 plus 19 is 29. 30 divided by 8. And 13 minus 19 is -6 divided by 4. -6/4 is halves. And so, yeah, anytime your answers are rational, as in they don't have some square root laying around, it turns out the original problem was factorable. But I chose this. I guess I kind of already explained it. I didn't like factoring it or testing further whether or not it was factorable. And here, over here, last part, AC method, AC, or no, I don't even have to do AC. Factors of 12 are 1, 12. Which of those had to be ocho? That's the 2 and the 6. And so I'll have an x with a 2, an x with a 6. 0. Plus. I break it up, right? 2 things multiply to be 0, so I can use product property. Therefore, one of these equals 0. I get x equals 2, or x equals -6. And so, kind of like what I was saying here, the fact that these have no irrationality to them means the problem was factorable. And I chose factoring because I didn't feel like doing the AC method, but I happen to notice this one's factorable. I recognized 12 had some factors that added to 8. Here, so I'm not going to solve these ones, but let's see if I could explain why. I think I would choose factoring here because there are factors of 12 that subtract to be 11. That's the 12. Over here, leading coefficient is 9. I wouldn't want an AC method, so quad form. Because, yeah, the leading coefficient. If that was equal to 1, then I would check for factorable. Oh, wait a minute. Guys. You could have done that. I thought one of these was a B term, but it wasn't. There's no B term. Proper. No B term. And so then I could solve using square roots. But yeah, quad form. I mean, like, yeah, eventually you can solve using whatever way you want. So I could have added 5 to both sides, divided both sides by 9, rooted plus or minus. Would have been good. All right, this one here. I don't. Not factorable. 5 times negative 1, 5. There are no versions of those that track to be 1. The fact that this is not 1 means I don't want to complete the square. The fact that this was odd, I don't want to complete the square, so quad form it is. And over here, let me rearrange this. X squared minus 2x. Oh, you know what? A is 1, B is even. This is complete. Comp the square. Boom. All right. Well, anyways, thanks for watching, internet friends. Good day. Have a great day. You've earned it.